work with finding the centroid of a region. Now, centroid is going to be somewhat closely related to center of mass. Centroid is kind of like the geometric average point in a region. Now, where it's different than a center of mass, it can be the same as the center of mass if your mass is of uniform densities. If you have a plate, sometimes it's called a planar lamina. So a plate that's uniformly dense throughout its region. But if you have something of a fluctuating density and you're trying to find like the balance point, then you're going to be trying to find the center of mass. Now for us, we're going to be trying to find centroids. So that is, well, what would be, the point there where you could put your finger to hold up, your little center of mass or your planar lamina. Now, we're going to start with this in kind of a nice finite way with just a few points and try and figure out, wrap our head around the center of mass. And it's going to involve several different calculations, one of which is going to be totaling up the mass. So the mass of our objects is written here on each of these points. So I got a total mass of 2 plus 4 plus 8. So it's going to be 14 for the total mass. And then I want to see the mass's effect in terms of rotating it around an axis. So for instance, this 2 here or this 8 here, how does it want to turn this around the x-axis? Now you might, the y-axis. You might be familiar with something from physics, force times perpendicular lever arm. The force is going to be the 8 here, the mass, and the distance here is going to be what we're going to multiply things by to figure out, well, what's the rotational force around this axis going to be? So in the y direction, you've got 8 is a distance of, 3 away? 1, 2, 3. So that's the force that it's going to exert or want to exert to rotate this around the y-axis. So you get that with 8 times 3. Let me just kind of highlight that this way. 8 times 3. What else do we have? Well, we've got a point here at 2. Now 2 is 1 unit away from the y-axis, but the important thing is that it's to the left of the y-axis. So that distance is a -1. So that's going to be this one here. And where's my orange one? I don't have my orange one today. Bummer. Guess I'll try it with the green one. Last but not least, we've got a 4 here. 4 is a distance of 2 away. So that's the combined rotational force that this y-axis is feeling based on these 3 points. So you multiply those together, add them up, we get a total of 30. We'll call that m sub y, the moment around the y-axis. You can play the same game for the x-axis. What's that rotational force around the x-axis? So this time, since 4 is below the x-axis, a distance of 1 away, its rotational force is going to be a -1 times that 4. Likewise, over here, the rotational force of this is just going to be 2 times 1. You're 1 above the x-axis. And last but not least, your y-axis, this point is 2 above the x-axis, and it's going to rotate with a force of 8 times 2. Now these totals are the first start of trying to find your centroid. To finish this up, to find the x-coordinate, we need to take its y rotational force, it's m sub y, and divide it by m. So m was our total here. That's how much mass we're dealing with. So if we take that force, 30 divided by 14, so x bar is going to be 30 divided by 14, or better yet, just 15 over 7. Oops, 15 over 7. In a similar way, we want to get y bar. So, I don't trust that one again. So let's do y bar. That's going to be m sub x divided by m. So again, we're going to be dividing by 14. This time we're going to have a 14 itself. 14 divided by 14 is going to give me a 1. So there's your center of mass here, or really the centroid for this. Well, let's see, I guess center of mass would be the appropriate term in this case for this region. Now what we're going to have to do is we're going to have to extend this to a continuous case, not a finite number of points, but an infinite number of points. That's where this problem transitions from, an algebra kind of problem that you can do, in a low-level physics class that doesn't require calculus to something that requires calculus, which is what we're going to work with. And I apologize that these formulas didn't show up too nice, but one thing that we're going to do is try and find the area of the region. That's going to be the analog of our m that we had here. Now we're going to take the area times the density. For us, in this class, and for our purposes, I'm going to assume that the density is 1. The density is going to be this rho term. Density. That's the density of your region. Now you might think, it's like, well, why are you bothering to assume that rho is 1? Rho doesn't have to be 1. That's true, but when you look at our formulas to find these coordinates for the center of mass, or excuse me, the centroid, what happens to the rho if it's here and here? Yeah, it's going to cancel itself out. And if you look, it doesn't really matter what rho is for these types of problems, because it is going to cancel itself out. Same thing for your y bar. Now, one thing to point out and to kind of keep in mind is that to calculate y bar, you're going to take the moment around the x-axis and divide it by m. To calculate x bar, you're going to do the opposite. Take the moment around the y-axis and divide it by m. That's going to give you your coordinates. Sometimes this point might be off of your region. That can happen. But it should just generally be in what you would kind of regard as the geometric center. So let's take a look at the first one here. Example A. So I got this equation here, 5x plus 4y equals 20. Let's see if we can't try and figure out, what's going on. And we're going to go back to something that I hope is starting to get a little bit familiar. We're going to cut ourselves a little slice here. And we're going to work with the area of that one slice to figure out its rotational influence for this. Now, first thing first, we want to figure out the area. So let's see if we can't find that area. I want to find the area of this whole region. Well, let's think. So I want the height of this times the thickness. What's the thickness of this slice? dx. So that's telling me I want to have the height, everything in terms of x. So I can solve this equation here. That would be y equals 20 minus 5x divided by 4. That's going to be my height times the thickness. So I can get the integral of 20 minus 5x over 4 dx. What should be my limits of integration for this integral? Yeah, 0 to 4. Keep in mind that this slice can be taken anywhere in this region. It can be taken as low as 0 or as high as 4, and you're still going to be in this region. So those are going to be our limits. Let me kind of keep these things color coordinated that way. 0 to 4. 0 to 4. So looking good there. Let's see. I'm not really going to be interested in you showing all the work for a problem quite like that. So what's the quick alternative to showing the work there or doing the work? Math 9, yeah. So out of courtesy to ourselves, let's just take the 1/4 out front. So I'll multiply the results by 0.25 or just divide them by 4. Let's work with the integral from 0 to 4 of 20 minus 5x. Sorry. I got to exit the limit here before I start typing in. 20 minus 5x dx. That doesn't look right. Yeah, I put a dt. I'm not sure how I got a dt there. But real quick, why do I know that this is wrong? Other than the fact that I get big numbers, but why do I know this is wrong? It's negative, yeah. So kind of a nice little mistake there, a little teachable moment. Let's do this one again and go back there and make that an x. Times 0.25, that's going to be 10. All right, let's think about the rotational force of this bar as we try and rotate around this axis. So I've got to find this distance here. I'm going to give myself coordinates of this point. Let's call it x and y. So x and y. Now the rotational force is going to be the area of this times its distance to the y-axis. So the force on this plate is going to be the area. And man, all my writing utensils are just not doing it today here. Area times the distance to the y-axis. Now, how are we going to calculate the area of that plate? Well, what's the basic shape of that plate anyways? This little slice here. Rectangle, right? And the area of a rectangle is just what? Base times height, width times length, etc. So it's just base times height. Now the base in this case is dx, right? What's the height? The height is y. All right, so we can put a y there, and that's fine. But what is that dx telling you? Yeah, we need to get it in terms of x. But the fact that we have a dx slice here, we need to get that in terms of x. So I'm going to replace that with 20 minus 5x over 4. And then a dx here. The last thing I need is the distance from here, from my slice, to the y-axis. So if this point has coordinates of x and y, what does this point have coordinates of? 0 and y. So what's that leave us with for this distance? X. That distance is just x. So distance to that axis, there you go. So that's the force on one, or force exerted by one plate, as it tries to rotate this region around the y-axis. Well, do we want just the force on one plate? Probably not. We need to add up the force on all such plates. So what's going to do it for us in that regard? What's going to add up the force for all such plates? Integral. So let's clean this up a little bit. I'll distribute it in the x. I'll take out the 1/4. I'll have 1/4 the integral of 20x minus 5x squared dx. And we're going to have the same limits as we did before. Those limits are going to be 0 to 4, like that. That's going to be m sub y, your moment around the y-axis. Now we got to do the same thing, except the moment around the x-axis. So it's going to be a little bit different here. Now, I'm not sure exactly how tall this is, but the force of this, because this is of a uniform density, can be thought of to be felt right here at the midpoint of this. So how would I find the midpoint of that? So again, if this is x and y, this is going to be x and 0. Where's the midpoint going to be? What's the coordinate of that point going to be? Well, it's going to be half of this distance, right? Y divided by 2. That's going to be where the force of this can be thought of to be felt. Is right here. Concentrate all that force there. So again, we're going to try and find the force on one plate. At some point, we're going to have to go back and calculate that numerically. But let's try and find the force on one plate. Now we're trying to find the moment around the x-axis. So let's think. That's going to be the area times the distance to the x-axis Okay. Well, the area is kind of what it was before, right? It's just still going to be y times dx, or this times dx. So that much hasn't changed. So it's going to be 20 minus 5x over 4 times our dx times the distance to the x-axis. So the distance to the x-axis is going to be y over 2. Okay, so y over 2, or 1/2 times y. And what happens when I have 1/2 times y? Well, I'm going to replace y by this expression right here. I'm going to take the 1/2 and the 1/4 all the way out in front. So 1/2 times 1/4 is going to be a 1/8. 20 minus 5x. And this is going to be y, which is going to be 20 minus 5x over 4. And then I have a dx here. Let's clean this up a little bit. Let's bring the 4 out in front and get 1 over 32. And then I'll have 20 minus 5x squared dx. Okay. That's the force, the moment around the x-axis. So let's see if we can't find that total there. That's going to be the integral 1 over 32 between 0 and 4 of 20 minus 5x squared dx. And now it's time to find a couple of these integrals. So let's see, for this first one here, I'm going to change that a little bit. Let's put in the 1/4. 1/4. And then I need to put in another x here. So let's insert second. Delete key allows you to insert. I'll insert an x. And then over here, I want to make that an x squared. So there's our first one. Let's turn that into a nice fraction. So it should be 40 over 3. Alicia, are you getting the same thing? Yes? Okay, thank you. And let's try the second one. So let's clear out that. I think I'm going to go all the way back up to the first one. So let's go all the way back up here. Press enter to copy that down. I need to make a couple changes. Let's see, I just actually kind of won, I guess. No, I can't get away with that way. All right, I need to put in a parenthesis here, and then another parenthesis here, and then square it. When I'm all done, I'm going to divide that by 32. So divided by 32, and hit the math key, answer a fraction, 50 over 3. Nice, nice. Let's determine both of our coordinates now for x bar and y bar. Now, oddly enough, or interestingly enough, depending on how you want to look at it, x bar is going to be m sub y divided by m. Y bar is going to be m sub x divided by m. Let's put in both of those and see what we come up with. So m sub y was 40 over 3 divided by m, which way back at the top was 10. If you're looking at that going, oh man, my brain hurts, I'm just tired of thinking about this problem, I have sympathy for you. You can get your calculator to do that. So it should simplify to 4/3, but if you're looking at that and not really happy, let's do a fraction in the numerator, 40 divided by 3. And then in the denominator, 10. That should come out to a nice, neat fraction of 4/3. So we get 4/3 that way. And then for the other one, y bar, let's see. I want to take m sub x. That's going to be 50 over 3 divided by 10, which is going to turn into 5/3. Whew. So that's about, 1 1/3 and 1 2/3. One thing you can do, it's tough to necessarily check these things completely, but you can look back and see if that point makes sense. Now, I think I've covered it up, but if you look back at your handout, you might see a little dot here. And that wasn't just a smudge, that's our actual center or centroid here for this problem. And it looks pretty good. Looks like it's reasonable balance point. You've got some mass that's a little higher up here, so you need to balance it out with a little lower point. This one, yeah, it looks pretty good. Is it a complete check? No. but at least it passes the first glance at this. Whew. All right. A lot going on with that one. Now you see why we're starting this today and not waiting to do it all on Tuesday. I'll pause for a second here if there's some place that you want me to go back, or if you just want to go home and put your head down and cry. I understand that too. So what do you got here? I could just do a quick recap if you'd like, if you don't have specific questions, or we can just move on to the next one. Yiming, any thoughts? Oh, we got a question here, Clyde?
Could you go over again why we're going halfway down that dx?
Yeah, that's where we're going to regard this, the force from this as being felt as the midpoint. Because it's being felt here to a greater extent, it's being felt here to a lesser extent. So we're just kind of taking the average of those to figure out and say, all right, well, we're just going to regard all that's force, its moment around the x-axis as being exerted right here. So that's going to give us a way to finish this calculation rather than try and stretch our brain about, well, this point's going to be taller, this one's going to be smaller, etc. So we're just taking the average. Yes?
How did you get the red x?
Oh, so that's just a distance. I just put general coordinates of x and y on this point. The distance from here to here is just the x distance.
Okay.
Yeah. So yeah, a little bit easier than what we have over here. This one, you got to feel that that distance is really going to be measured from the center there. So it's, yeah, that part's a little tricky. Yeah. Anything else? So kind of as a recap, there's a few little goals that you can have, intermediate goals, a point or two for finding the area, and then you want to try and find the moment around the y-axis. So that was our next goal. That's going to be figuring out x times this area, and then add it all up for all the possible slices of dx you can take in this direction. Then we did the same thing for the moment around the x-axis. The tricky thing about the moment around the x-axis is that its pressure is felt at the halfway point. That's where we're going to regard it as. So that's where our calculation was, and it worked out pretty good. Remember at the end when you're calculating x bar and y bar that these numerators kind of are mismatched with these coordinates. Whew. All right. So, Ethan, what's my famous line at this point?
That was easy.
Actually, I was thinking, don't worry, I put no more than 7 or 8 of these on an exam. So,
Forgot some old spot.
yeah, forgot. No, this one, and yeah, I'll be very candid with you. When I got down to the end, I breathed a little sigh of relief because I hate it on these things when I make a mistake and have to go back like 10 steps and like, can you erase this and do that? And then you get some students that are very patient and then they'll politely erase. And then you get the people who are a little bit more mad and who do that. And then you get the people who are really pissed off and then throw something down on the floor. And I just feel so bad. I'm like, all right, I know I screwed up. So anyways, I am human. Cut me some slack if I do make a mistake. All right, let's move on to another one. Get you a couple of these. And if you remind me at the end here, I'll open up the homework as well. So that way you can get started on it earlier. Let's see. All right, so on this one, now that we've gone through this one, start trying to help me out with this a little bit more in terms of, figuring out what comes next. The first place to start would be with a little slice here. So let's calculate a slice. Actually, before I even calculate a slice, what's the first thing I calculated with the last one? The mass. Yeah, the total mass, the area, basically. So the mass is going to be proportional to the area. It's just going to be the density times the area. So let's find m for ourselves in this case. Now it's going to be a little bit easier than the last problem. It's going to be easier because we've already got y solved for. What do I have to do to figure out what y is? Or excuse me, not y, but the mass. Yeah, integral. So I'm just going to integrate from, I don't know, let's say 1 to 4 of 3 over x dx. And I don't think it's going to be quite as nice as it was in the last one. That's going to be 3 times the natural log of x between 1 and 4. Or it's going to end up being 3 times the natural log of 4, essentially. 3 ln of 4 minus ln of 1. Now, ln of 1 you should be familiar with. What's the natural log of 1? 0. Thank you. Appreciate you making me look good. All right. Now, just for convenience here, let me bring that 3 up and regard it as ln of 4 cubed. Who's got it 4 cubed? What's 4 cubed? 64. All right, so we're just bringing that up there. So maybe it's just a little bit more convenient to carry this term around as the log of 64 as opposed to 3 ln of 4. We'll find out. Okay, let's take a little slice through this region and start calculating some moments. We'll start with the more friendly one, which would be the moment around the y-axis first. So we got a nice little slice here. What's the thickness of my slice? dx. And I'll give this coordinates of x and y to find the moment, to find the force that this exerts around the y-axis. I need to know a couple things. One of those things that I need to know is what's that distance, and I'll just do that distance here. So the moment around the y-axis is going to be the area times the distance to the y-axis. See if you can't fill in that distance to the y-axis for yourself. Fill in the area for yourself. If you're watching this later, pause the video. Try and fill in the expressions for both of these on your own. What's the area of this slice? Y times dx. Good. Paul, how about the distance this slice is from the y-axis? How far is it from the y-axis? No, not quite. I mean, this coordinate is a general coordinates x and y. Its distance to the y-axis is just, well, let's see. This would have coordinates of 0 on y, because you're right on the y-axis. Yeah, thank you, just x. Now, this is telling us something important. Andreas, what is this telling us that we need to take note of? Yeah, we want everything in terms of x. So that's what that dx term is helping us remember. So we can simply replace y by 3 over x dx times x. Isn't this special? What do we end up with? 3dx. Nice. Nice. So putting all that together, I want the integral of 3dx between 1 and 4. And that's just going to be 3x between 1 and 4. I don't even think we're going to bother to do f and int on this one, right? This is going to be 12 minus 3 is going to be 9. Nice. So let's leave that part aside here for a moment. All right. Let's try m sub x. M sub x, let's see. Again, it's going to be area times the distance, this time to the x-axis. All right. Help me out. Where is that distance to the y-axis going to be felt? The midpoint. So that has coordinates of, say, x and y over 2. Okay. Let's see if this one works out pretty nice. That area is going to be kind of the same thing as before. It's going to be y times dx. Can we just jump to the chase here, or does it help out if I write y times dx? I'll write y times dx. Personally, I err on the side of showing more steps than not. When you're doing these things, you don't have to show me every step. Just as long as I can follow the logic, that's fine. Y times dx times that height, or the distance that that's felt at, which is going to be y over 2. But that dx term is really telling me I need everything in terms of x. So y was 3 over x dx, and then this is going to be 3 over x divided by 2. So let's see if we can't clean that up. That's going to be a 9 halves out in front. 9 halves times dx over x squared. All right. Let's go a little bit further with this one. Let's find the total force, the total rotational force around the x-axis. So that's going to be the integral of 9 halves from 1 to 4. Let's just do x to the negative 2 dx. I'm not sure I feel like fussing with that. That's a polynomial type term, so let's just try to do the happy ending thing here with f and int. 4.5, math 9, 1 to 4. This time I want to do x raised to the negative 2 dx. 3.375, 27 over 8. So 27 over 8. last but not least, let's plug that into find x bar and y bar. So x bar and y bar are going to be m sub y over m and m sub x over m. Let's take a look at m sub y. M sub y was 27, no, that was just 9, right? So 9 over natural log of 64, and then 27 over 8 divided by ln of 64. Let's get a couple decimal values for these things, because I have no idea what these numbers would look like. So the first one, 9 divided by ln of 64. And the second one, 27 over 8. So 27 divided by 8. I'll put that in parentheses and then divide by ln of 64. Ln of 64. And bam. So 2.16 and 0.811. Again, you can look back at your graph and make sure that those kind of make sense. The point that we came up with matches the point that I put on your handout for you, right there. So, looking good. A little bit north of 2, a little bit south of 1. Looking good on that one. How are you feeling about these things? A little bit better, maybe, hopefully. We'll do maybe one more next week, just for the practice. But take a look at these over the weekend. They're tough. They're tough. Have a good one, and